So I'd like to thank the organizers, Pierre and Fernando, for their hospitality. And also, I'd like to thank them and my advisor, Laurent, for giving me the opportunity to talk in such a nice place. So, the topic today is on rigidity of steady gradient Ricci soliton. And before stating the theorem we want to prove, we should recall the definition of a steady gradient Ricci soliton just to fix notations. So, a steady gradient Ricci soliton, which we write by laziness SGS. It's triplet MNG nabla F, is a Riemannian manifold MNG endowed with a potential function F, which is smooth from M to R, such that, can you read here? Such that Ricci equals the Hessian of F. So basically, the idea is that when we study such soliton, the topology is contained in this term, and this term contains geometry. It's the basic idea, and the two interferes. Just to be more precise, from now on, everything is complete and has bounded curvature. Okay. So we should state the theorem we want to prove. So let MNG nabla F be a steady gradient soliton such that first we require that the sectional curvature is non-negative and it's non-flat. And secondly, the scalar curvature is in L1 of MNG. These are the assumptions. The result is Mn is isometric to the cigar metric cross times the Euclidean space of dimension n minus 2 quotiented by the fundamental group of Mn, and pi 1 of Mn is a B-bar group of rank n minus 2. So B-bar group, it means that it's a subgroup of isometries of the Euclidean space of dimension k. Let's say if we have a B-bar group of rank k, and if you take the quotient of the k-dimensional space, Euclidean space, by this group, it gives you a compact manifold. Okay, so before embarking in the proof, we should state several remarks. So maybe for one who does not know the cigar metric, so
what is sigma
2? Yeah, I'm going to, it's the cigar, and I'm going to to define it, even if Detangzhu has already defined it. So cigar metric on R2 by Hamilton, and given by, so in Euclidean coordinates, it's conformal to the Euclidean metric dx2 plus dy square over 1 plus x square plus y square. In radial coordinates, it gives, of course, dr square plus r squared d theta square over 1 plus r square. And in special radial coordinates, which are the best one to understand the curvature decay, it can be read as ds square plus hyperbolic tangent square d theta square. And so it looks like at infinity a cylinder. Okay? And to make sense of the name cigar, it's like that at the end, or at the beginning, as you want. Okay? Right. And scalar curvature is exactly, I think, 4 over the hyperbolic cosine to the square. So in particularly, it is big O of exponential of minus 2s. So it shows the exponential curvature decay. And as at infinity, it is isometric to S1 cross R, nearly isometric. The circle has nearly constant radius, so that we can see easily that for the cigar, R cigar is in L1. Okay? Okay. Now, we should mention several remarks. So first, for n equals 3, we should, it's true if n equals 2, but it has already been done without the assumption of curvature decay, okay? If n equals 3, by Hamilton IV estimate, the first assumption is always true, okay? Assumption y is always true. All right. Secondly, the Bryant soliton is not in this class of gradient soliton, okay? For the one who knows it, Bryant soliton. So the scalar curvature of the Bryant does not belong to L1 of L1, let's say, okay? Even it has positive operator curvature operator, sorry. Yeah, the Bryant soliton is not a... The decay of the Bryant soliton is nearly 1 over R, and the volume of the ball is approximately R to the power n plus 1 over 2. Okay. So, lastly, an interpretation of this theorem is as follows. We can see this as a gap theorem, okay? Theorem 1 is a gap theorem, let us say à la Greenwood. In the case of steady gradient soliton, for steady gradient soliton, because during the proof, I mean, now we can't see it easily, but during the proof, we can think about a curvature decay of the type one over r to the power 1 plus epsilon. Epsilon strictly positive, in fact. Okay? We could have thought about this, and the proof works. I mean, it's not really the same, but the idea is the same. And then this means that it is gap theorem, in fact, because under these assumptions, the theorem is true, and in fact, we have exponential decay. So there is a gap between the curvature decay of, let us say, the Brian soliton, which is one of the R, and the exponential decay in the case of non-negatively curved spaces. Okay? So now we can embark for the proof. There are two steps. First one deals with the topology of the levels of F, and it has nothing to do with the non-negativity sectional assumption. And the second, of course, will rely strongly on this assumption. Okay? So, first, the topology of the levels of F. Okay. So we have a family of levels of F, and the idea here is to take a blow-up of these hypersurfaces to infinity. And we hope that at the end we will get a limit which is diffeomorphic to the levels of F. But we have to take care about some geometric control on these levels of F. So before stating the main proposition of this section, we should recall the link with Ricci Flow, right? Will be very important. So we have, our assumption is that we have a steady gradient soliton. So it remains to solve the differential equation given by the vector field minus nabla F in this case. Be careful. Then define the curves of metrics in the following way, which is the pullback of the initial metric. Then we can easily check that GT solves is a solution to the Ricci flow, okay? And when we have bounded curvature, it is an eternal solution. So it is defined on R. So as Detangzhu said last time, in particular, we have two cases, Okay, the positive scalar curvature or Ricci flatness. Okay, so we will deal only with this case. Be careful. I think that the study of Ricci steady gradient soliton has nothing to do with flat matrix. I mean, it's more rigid, as you can see, and we know that Ricci flat matrix is a highly non-trivial fact and is studied too. Okay, so it's not the same method. So we will deal only with this case, even if in our study we will call this case a trivial one. Okay. First, let's state the proposition we want to prove, okay, about the topology. So let MNG nabla F a steady gradient soliton such that positive scalar curvature plus non-negativity of Ricci and the curvature operator tends to 0 at infinity. And third, R is in L1. Then we know the type, the diffeomorphic type. Empty, which is by definition the level of F, will be diffeomorphic to a compact flat manifold of dimension n-1, okay? So when we will finish the proof of the theorem, we will see that the assumption of the theorem implies these, okay? So let's embark for the proof. Should state several lemmas before taking Shiger-Gromov limit. So first, a lemma which is essentially due to Carrillo and Ni. So steady gradient soliton such that we have non-negativity of Ricci, positive scalar curvature, and limit of scalar curvature at infinity is 0, okay? Let us say like that. It's more or less the same statement. Then we can say that the steady gradient soliton has finite topological type, and moreover, so there exist geometric constants like that, which depends on the manifold and the nabla F potential function equal 1 to 6, such that the gradient is bounded from below and from above by positive constant first, and secondly, F is linear in R. Let's say C5 to the distance plus C6, and is bounded from below by C2, C3. Okay, it doesn't matter, but write it. Plus C4, where R of P is a maximum, okay, for the scalar curvature. Right. So it says that F is proper, okay, and in particular, F, I mean, we see F as a Morse function, okay? So MT, the levels of F is well defined, in this case, compact hypersurface. So for t strictly, or t positive, where 0 is assumed to be the minimum of f. Okay, we can always assume that. Because remember, if we give a sign to Ricci, it is given a sign to the Hessian f, and it will give us a convex function. And the minimal set is exactly the critical point of f. Right, and moreover, MT is connected by Shiger-Gromov splitting theorem. Shiger-Gromov splitting theorem. Okay. Now we want to control the geometric datas of this MT. Okay? Next lemma deals with that. So, under the same assumption, as in lemma 1, we have an estimate of the volume, okay? So we call it A, like area. A of T0 is less than A of T is less than A of T0 plus the integral of the scalar curvature over the domain F minus T0 T. Okay. First, and secondly, a control on the matrix for T greater than T0, always positive, okay. And we have control on the matrix, okay. It's increasing with T. And a result which relies on this is that the injectivity radius of the MT, the GT, be careful, T is not is now a time, okay? It's space, I mean. I should have written tau here, okay? Do not mix it up. Is greater than the minimum of the injectivity radius of MT0 and pi over the maximum the sectional curvature of T. Okay. So you see that the assumption of being in L1 appears quite naturally here. I mean, if you suppose that R is in L1, you bound the volume of your hypersurfaces. Okay, I should write it. A of T is, by definition, the volume of the MT, okay? We should sketch the proof of this. It uses two tools. One and two. Sketch of one. So apply the first variation formula to the MTs. It gives so the derivative of the area equals the integral over the hypersurface. The second, the mean curvature of this hypersurface divided by the norm of Nabla-F, okay? And here, HT, which is the second fundamental form, equals the Ricci over the norm of Nablaev, okay? Maybe for some people the convention is the opposite, but it doesn't matter. The second fundamental form. Okay. Right, so we just have to compute A prime of t equals scalar curvature minus Ricci evaluated on n, which is the unit pointing outward normal to the hypersurfaces, over the square of Nablaev. Okay. So clearly, as Ricci is non-negative, this is non-negative, okay? So we have this. We can integrate, okay, immediately. So it gives a of t0 less than a of t less than. So here, get rid of this term, and by the co-area formula, we get the result, okay? F minus 1 t0 t plus a constant depending on ct0. Yes, I've been maybe too fast. Constant of depends on t0. Scalar curvature. Okay. Use the co-area formula. Okay. So maybe I should keep this. So now we want to apply Shiger-Gromov's compactness theorem. Okay. So, end of the proof of proposition. So under the assumptions here, so we should write star. So under star, the family of hypersurfaces belongs to the set of compact Riemannian manifold such that it exists for t greater than t0, which is fixed volume bounded from above and from below by positive constants. The injectivity radius is greater than some positive constant, uniform positive constant, and the derivative of the curvature operator are bounded by, okay, everything depends on t0, right? That, and here too, for any k. So I'm cheating here a little bit, in fact, because we did not prove this. I mean, and because of the magic of heat equations, I mean, because of the Ricci flow, it's smooth, the metric, okay? And so we can assume that at time 0, on the steady gradient soliton, we have bounded covariant derivatives of the metric. And then, as the second fundamental form depends on the curvature operator, we can also prove that the covariant derivatives of the curvature operator of GT, be careful, is also bounded, okay, uniformly, but for T0 fixed. So, by Shiger-Gromov compactness theorem. You can extract there exists a subsequence MTK, GTK, which converges to a smooth manifold M infinity G infinity of dimension n minus 1. Okay. And it's compact. So in a C infinity way, okay? C infinity topology. And because of this, we know that for TK large enough, the hypersurfaces will be diffeomorphic to M infinity, okay? So if we know the diffeomorphic type of infinity, we are done. But there is one assumption we still did not use, is this one. And moreover, what one can check by Gauss equation that the curvature operator of the GT tends to 0 as t goes to the plus infinity. Use Gauss equation, but we will recall these equations later. Okay? So we are done. And the proposition, okay? Right. So we note that we have not used the non-negativity sectional assumption, okay? We just deal with Ricci curvature. So should erase this, and now we can begin. I'm a little bit elliptic, but okay, when half an hour. The second part, so end of the proof of the theorem. Now assume all these assumptions, okay? Okay. Double star. From now on, we assume double star. Okay. First, we will use the non-negativity assumption 3 times and 3 different times. Okay. First, we won't use the previous proposition. Okay. So we just want now a global splitting. Okay. The first step is to obtain a global splitting of the manifold. So global splitting. So be careful. Do not use the first part. Okay. So when we want a global splitting, it would be nice to define a good subset of the tangent bundle, okay? And here, the most natural one is the kernel of the Ricci tensor, with natural in the sense of Hamilton, okay? So define a space-time p tau. Now tau is time, okay? P is a point, which is the set of vector in the tangent space such that Ricci of the metric at time tau v equals 0. Just mean that it's the kernel of Ricci at the point P. P, so in Mn cross R. Okay. So recall that the sectional curvature of this matrix is always non-negative because the flow acts by isometries. Okay? It's very important here because we don't know that if the non-negative sectional curvature condition is preserved. In fact, Laney has found a condition, a necessary condition to be for that condition to be preserved. And but in this case, works. And second fact is that the Ricci tensor satisfies a nice heat equation, which is so the time derivative of Ricci equals the Lishnerovich Laplacian of Ricci, where Laplacian of Lishnerovich acts on two symmetric tensors. So in coordinates, it gives the Laplacian, the rough Laplacian of the tensor, plus 2 times R y k l j t k l minus the symmetrization of the tensor, the tensor product of the Ricci one, so R k t l j minus R j l t I k. I hope that I did not make a mistake. So under these remarks, Hamilton, in his seminal paper of four manifolds with positive curvature operator, by Hamilton's principle, I mean maximum principle, we know that eta is a smooth distribution, and especially it is invariant. What we want is that is invariant by parallel transport. This is the most important thing. We get. So now apply the Rams Theorem in his strongest version by the Rams Theorem, stronger one. We have a splitting of the universal cover. So M tilde N is isometric to M1 to the power k of dimension k, G1 times M2 n minus k, G2, where the tangent bundle integrates Tm1k is exactly set of Ricci strict of positive vectors, and Tm2 n minus k is exactly set of null vectors, kernel, okay, is eta. But as we have non-negative sectional curvature, M2 is flat, and the universal cover means that it's the Euclidean space of dimension n minus k. So we get, first step, M tilde n G is isometric to M1k G1. We don't know the dimension now. times A are the Euclidean space of dimension n minus k. Okay. All right. So what remains to prove is that k equals 2. Okay? If we know that k equals 2, we are done, because the only steady gradient soliton of dimension 2, which is not trivial because we have this condition, is the cigar. And the third step, but we won't have time, I think, to prove it, is that the fundamental group is a B-bar group of rank n minus 2. Okay. Second step, and we will use the proposition that has been erased. So claim k equals 2. So on the one hand, Gauss equations tells us that the sectional curvature of the GT matrix equals the sectional curvature of the global manifold restricted to this plane, to this spherical plane, plus the determinant of the second fundamental form restricted to the same plane. X, Y, parallel to TMT. Okay? So by the assumption, the sectional curvature is non-negative, because the global sectional curvature is non-negative, and as, if you remember, the second fundamental form is in terms of Ricci, so it's non-negative 2. Okay. We'll be brief. That's the first remark. The second step consists in, so on the other hand, as I said, the proposition 1 tells us that under certain condition we have that empty is diffeomorphic to a flat compact manifold, and we have to check that these conditions implies those of proposition 1. Okay. So, in fact, we just have to check that if we have these assumptions, the curvature operator tends to 0 at infinity. Okay, it's this only assumption we have. So, to have that, by the theory of non-negatively curved manifold, essentially due to the existence of Shara-Fudinov retraction, Shara-Fudinov retraction for manifold with non-negative sectional curvature and bounded non-increasing map from Mn to a sol, but I won't go into details here. Non-increasing. We know that we have positive injectivity radius of the manifold, the global manifold. In fact, we can be a little bit more precise. We have an estimation from below, but we don't care here, okay? So if R is in L1, I mean, the limit of scalar curvature is 0, okay? Like this, and the fact that, I mean, R is a Lipschitz function, okay? And therefore, as we have non-negative sectional curvature, limit of the curvature operator is 0. That's right. So, by proposition 1, empty is diffeomorphic to a flat, compact, n-1 manifold. Okay. So what's the point of all of these remarks? So now we conclude by a rigidity theorem for compact manifold with non-negative Ricci curvature, and using a strong theorem on compact flat manifold by Bieberbach theorem. I mean, there is a finite covering of these compact manifold, okay? Because it's a flat compact manifold. Right. So, by one hand and the other hand, we have on an n-1 dimensional torus matrix with non-negative Ricci curvature. And so the Bachner theorem in the equality case told us that the metric is flat. Finally, I mean, should by I don't know. 1, 2. 3 stars and 4 stars by non-negativity of Ricci curvature and this plus Bachner theorem in the equality case, meaning that we have the first Betti number, maximal first Betti number, B1 equals n-1. GT is flat for T positive. So let's get back to the cos equation. You have 0 there, and it was non-negative, so the spherical sectional curvature vanishes, and this also vanishes. So we have to traduce this algebraically, and it will be the third and final step. So, I mean, the second step was to show that K equals to the same step, all right. Therefore, Gauss equation implies that the spherical sectional curvature vanishes whatever be the plane in the tangent bundle of MT, and determinant of the second fundamental form restricted to xy equals 0, 2. Right. What does it give? So let's name them A and B. A gives us that the scalar curvature, by its very definition, scalar curvature of G, is equal to 2 times the Ricci tensor evaluated on the unit pointing outward normal. Shall I write it again? Okay. And by the assumption it is non-flat, it's strictly positive. Okay. And B tells us that dimension of eta p tau, so it's the kernel of a Ricci curvature, is greater than n minus 2. So we have to check that we have an equality here. So this means that it cannot be, of course, n. Okay. And the second, the mean curvature, ht, I should say as, ht equals, so r minus Ricci of n, where n is that, divided by the norm of nabla f, by a. We know that it equals to r, the scalar curvature, divided by 2, norm of nabla f, and it's strictly positive. Okay? So the trace of the second fundamental form is strictly positive. Therefore, we have 1, and the dimension of the kernel, should write it now explicitly, is equal to n minus 2. Dest k equals 2. So managed to get what we wanted. Okay. And we should mention several remarks now to end the proof. So further remarks. We have shown that m tilde of m is isometric to a surface, okay, G1, cross the Euclidean space of dimension n minus 2. And the structure of steady gradient soliton goes down to each factor, in fact, okay? And therefore, sigma 2, G1 is a steady gradient soliton of positive curvature, because it was the set of vectors, this tangent bundle is the set of such that the Ricci tensor is positive. Classification shall always be done by Shaw, Bennett Shaw, and other. Sigma 2 G1 is the cigar. Right. Sorry for that. And we should end by the fact that it remains to prove this. Okay. So it's a little bit more tricky. So it remains show that phi 1 has rank k, is rank n minus 2. So for that, we use solve theorem, and we follow closely, in fact, a paper of Green and Wu on metrics which are flat outside a compact set. Okay, we use solve theorem plus techniques of Green, Wu. See the paper of I don't remember its name, but okay. Went like that, and I think it's the end of the talk. So thank you for your attention, and